ちは。
こんにちは。
This campus is too big. I can't wait till they install, like, at the airports they have those, like, moving floor.
Oh, the moving walkways.
They should get, like, in the future here, we're going to have those.
Well, if you're going to do that, why not just have, like, that automated train system that goes around campus, and you can just, like, hop on, just like a rail system. And
Just on the outer edge.
yeah, there you go.
Just trying to get from one side to the other so far. At least an escalator at the stairs on the side of the mountain. 'Cause that's the stairs kill me. Oh, he did.
All right, let's get started. Sorry, I didn't realize it was time to start already. Who'd like to start us off with a prayer? Thank you.
Dear Heavenly Father, we thank you for this day. We thank you for the opportunity to come here and learn more about Campus 2 and expand upon our knowledge that we have in the previous years. And we ask you for lessons that will understand different concepts and we have the gift of interpretation to understand the textbook and the videos and our instruction given by Brother Corey. Please help us to be able to balance out our schedules as all of our classes are beginning to come to their end, and we may be able to prepare ourselves for the finals next month and have a great holiday and safety and grace. Jesus Christ, amen.
Thank you. Okay, so the iClicker warm-up problems. Find the equation of the tangent line to the function square root of x at x equals 4. So. can use whatever method you want on this problem, so you don't have to use stuff you're learning now. You can use whatever you knew how to do from Calc 1. If you see the connection to what we're learning in this section, that's awesome. Okay, snap if you need more time. Take one more minute. Okay, 30 seconds. So, if you guess, you have a better chance of getting it right than most problems. There's actually 2 correct answers. All right. Okay, so we're going out. Well, then you only have to figure out which 2 are equivalent, and then you know you pick one of those. All right. So, okay. We'll come back to this problem. So, today we're going to build off of what we did. Can you hear me okay? Today we're going to build off what we did on lab on Tuesday, okay, where we were trying to find polynomials that approximated these kind of ugly functions of e to the x, sine of x, cosine of x. But I know not everyone was in lab, and so we're going to do a brief review of what we did in lab, just to make sure we're all on the same page, okay? Before we go and dive back into the iClicker problem and move on. So for those of you that weren't in lab, we talked about approximating a function like e to the x at x equals 0, around x equals 0 with a tangent line. So you can do the process that you just used. You can figure out that the derivative of e to the x, derivative of y equals e to the x is e to the x. Y of 0 is 1. Y prime of 0 is also 1. Okay? Then you can use y minus y sub 1 equals m times x minus x sub 1. You can use the point slope formula. And the slope of m is 1. You get x minus 0. Here you get y minus 1. So you end up with y equals x plus 1. And, oops, that's the wrong one we want. If this thing will load. Come on, go. How come I can't do this? Take 2. No. It fluctuates. The number of tabs I have open at any one point is a random variable between 3 and 20. So no. So my mom had 72. What is wrong with this? My word. Okay, well, I won't be able to graph it for you, I guess, today. If we were to graph it, you get y equals e to the x like that, and you have the equation of the tangent line. See, the graphing would be better. Moves along like that, and we're pretty good in this area. So, but the question is, how can we get something better? Well, instead of using a line, we could use a parabola. Why? A line will match the point that it goes through and the slope that it's at right there, but a parabola could match the point and the slope and also the curvature. We can match the concavity there. So maybe if we did a parabola, we could get a better fitting curve. So let's work on that. So a good fitting parabola, so it would go through the same point. It would have the same first derivative. And it would have the same second derivative. Okay, this will give us as e to the x at x equals 0. Okay? That way we go through the same point, we have the same slope, and we're curving at the same rate. So, so let's figure out what those might be. We have some polynomial of third degree. We already know it's going to be 1 plus x plus something x squared. This 1 plus x, that's already the equation of the line that we found. Now we're just adding on a quadratic term. And we need to figure out what that coefficient is. And we're going to try to pick a coefficient so that the second derivative at 0 is the same for e to the x as well as this polynomial. So the first derivative is 1 plus 2ax. The second derivative is 2a. And to figure out what a is, what is the second derivative if f of x equals e to the x? What's the second derivative of e to the x at 0? It's just 1, because the derivative of e to the x, any derivative is e to the x. So if we plug in 0, we get 1. So 2a has to equal 1. So what do we know? A has to equal 1/2. So we could get a better approximation. Maybe e to the x is about 1 plus x plus 1/2 x squared. Should we see if the graphing facility is working yet? It's my keyboard that isn't working. I don't know what's wrong. All right. Okay. Well, why stop with a quadratic? Let's go to a cubic. If a quadratic is better than a line, maybe a cubic will be better than a quadratic. So then we could try a new polynomial. 1 plus x plus 1/2 x squared plus some coefficient for x cubed. And we can do the same process. We can take the third derivative. Well, we already took the second derivative up there. We really just have to focus on this term. You're going to have 3ax squared. Then for the second derivative, you're going to have 3 times 2 times ax. And the third derivative, you're going to have 6a. And what do we want the third derivative to equal? We want the third derivative at 0 to be the same as the third derivative of e to the x at x equals 0. And what's the third derivative of e to the x at x equals 0? 1, because all the derivatives for e to the x are e to the x. Plug in your 0, you get a 1. So when is 6a equal to 1? A is 1/6. So now we get a new polynomial. Okay, so this process is one we started on Tuesday, and this is the process you're going to be using for your homework to find approximating polynomials. Okay, these are called Taylor polynomials. That's why we use a T right there. Taylor polynomials. There is a pattern here. What do you guys think the next term's going to be? What do you think the coefficient is going to be for x to the 4th? 1 what? 1/24th? Some of you already did this if you went to lab. Where does this 24 come from? If we want the coefficient to be 1, when we take the fourth derivative, if we want the fourth derivative to be 1, then we have to divide by 24, because when you take the derivative 4 times, you're going to have to do the power rule 4 times, and you're going to have 4 times x cubed, 4 times 3x squared, 4 times 3 times 2x, then 4 times 3 times 2 times 1, and that's going to be multiplied by 1 over 24. They will divide out, and then you'll have a fourth derivative, the fourth derivative of just 1. So in this formula for e to the x, we're always dividing by the nth derivative. So e to the x raises the question, is that really equal to this sum? Oops. x to the 4th, 5 factorial x to the 5th, dot, 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 dot. If you keep doing that, that's what you end up with. So you get e to the x is equal maybe to this sum of x to the n over n factorial going from 0 to infinity. Okay. What's 0 factorial? 0 factorial is 1. Why is 0 factorial 1? It's a lie? It's a law. We did define it to be 1, but it actually makes a lot of sense to define it to be 1. So if you start with 4 factorial and you want to go backwards to 3 factorial, what do you do to 4 factorial to get to 3 factorial? You divide by 4. What do you go do from 3 factorial to get to 2 factorial? You divide by 2. So 2 factorial divided by 2 gets you 1 factorial. If you continue on that pattern, 1 factorial divided by 1, well, that's 1. So to keep that pattern alive, it makes a lot of sense that it should be 1. There's actually lots of reasons why we would define it to be 1. Okay. Brian, you had a question. You're getting a little ahead of us. I might not get there today, but yeah. If we don't get there today, we'll talk about it Monday. Okay. Yeah. So Brian's already thinking like if for x equals 1, you get e here. On this side, you get that, and on the other side, you get 1 plus a half plus a sixth plus a 24th plus a 1/20th dot dot dot. Does that equal e? Does it really equal e? The sum of 1 over n factorial, n equals 0 to infinity? Does that equal e? Well, if you look in your notes, the very first day we did series, I actually put that series up there. I told you that it actually does equal e. We might start by asking, does that series converge? Does this series here converge? It does. What test? You could do the ratio test, and you would get you'd get 1 over n. It would go to 0. So you could do it by the ratio test. So you could also do a comparison test to 1 over n squared once n is 2. So okay. All right. See if any of these are working. Okay, we'll see if this is working. Okay, here's our e to the x function. Okay, it goes through the x equals 0. I'm sorry, it goes through at x equals 0, it goes through y equals 1. We could approximate it with just that constant. It is 1 at that point. The line y equals 1 is one approximation, but it's not very good. If we go out to our 1 plus x, the equation of our tangent line, you can see that it's better. Okay? What if we go out one more degree? There is our parabola. So pretty good approximation for maybe about a negative 1/2 to 1/2. Oops. What? Yeah? We'll get to that too. So you have to tell me like what interval you care about around the center, and then we can decide how many terms you'd need to get within a certain accuracy. So you tell me what numbers you care about plugging in or using, and you tell me what accuracy you want, then I know how many terms to give you. Okay? So look what happens as we keep going out and getting more and more terms. it looks like it more accurately approximates that function. Will it eventually become the same line? So one way of saying that mathematically is, does this series, this weird series with x's in it, does that actually converge to the term line e to the x? It does turn out to be. So let's look at another. Okay, so here's sine. We're centered at 0 here. So we do go through the line y equals 0. There's the tangent line is just y equals x, because the slope is 1 right there. What's the best fitting quadratic? It's the same thing. So I'm at the second degree here, the way that I've set this up, but I'm right on an inflection point. The second derivative is 0 there, right? Second derivative sine's a negative sine, and at 0, that's 0. So the coefficient to my x squared term is actually 0. But what about a cubic? Let's go out a little bit here. Okay. And what about a fourth degree polynomial? The coefficient again to that fourth degree is 0, because the fourth degree of sine is, you're back to sine, and sine at 0 is 0. What about a fifth degree? Sixth, nothing. Seventh, ninth, 11th. Okay. Cosine. Oops. So here, my best fitting, the constant is just 1, but what's the slope of the tangent line there? 0. So even my first degree polynomial is going to just be the line y equals 1. It actually fits pretty well right there. But then if I go to a quadratic, you can see I get something better. Third degree, I don't have a third degree term. Fourth degree, sixth degree, 8th degree, 10th degree. Okay? Right. Let's do one that's a little bit different. So talk to your neighbor. What do you think is going to happen as we get more and more degrees to this polynomial, this Taylor polynomial? We're approximating it right here. Okay, talk to your neighbor. Make a conjecture about what's going to happen. All right. Let's see what happens. So you have a line. No quadratic. There's a cubic. So we are looking at, so this is actually a 5th degree polynomial. No 6th, no 7th. Oh, there is a 7th. So we went from 1st, 3rd, 5th, 7th. So we're at odd powers. Oops. This might be a little bit heavy for us. Oh, dang it. It locked up on me. Oof. it's not doing a very good of it's doing maybe a pretty good job of approximating that center section, right? Right here, but it's not doing a very good job over here or over here. And no matter how many terms we go out, we might be close here to the green, this center section, but if I'm outside here or there, it's not going to help me. So this is what we would call the radius of convergence, the area where this series is valid. Oh, darn it. There was one more important thing we needed to use this for. Like the series that we got here, it would only do a good job of approximating it from a minus pi halves to pi halves. That's the only thing we could use it for. Okay, so not all series work for all x's. Yes? It converges for all x's. So we'll spend a lot more time, probably in a few more days, talking about like how do you know which x's you can actually plug into these series and get a value out. So yeah. That's one of the problems. One way to think of it is it's got to try to get that infinite slope, at one point, and once it's trying to do that, it can't really do much to get beyond that, right? If you're trying to get a polynomial that gets infinitely high, it's not going to go infinitely high and then come back down to get you stuff. So, yeah, so that discontinuity causes a problem. Okay, so what we're doing here, okay, let me talk a little bit big picture here. What we're doing here is we're finding polynomials that we can use instead of these ugly functions, e to the x, sine of x, cosine of x, tangent of x. And you might say, but Brother Corey, they're not ugly functions. I like sine of x, and in fact, some of those coefficients that we had to use on those polynomials were pretty bad, right? But here's the question. How are you going to calculate sine of 1? Or when you plug in sine of 2 degrees into your calculator, what does it do? Your input is 2 degrees. What does it do with that 2 to get out that number? There is actually no sine function in your calculator. It uses these polynomials. So all it does is it takes these polynomials and uses those and takes it to different powers and uses those coefficients and then spits out the answer. So to figure out what sine of something or e to the something is or cosine or even like square roots, like you have to at some point when you're doing calculations get down to working with binary numbers on the register of the computer. Okay, and if you're working at that level, add, subtract, multiply, divide, you can handle pretty well. And if you can do multiply, you can start doing powers, okay. But when you start doing fractional roots, when you start doing sine, how are you going to do that? So if you can build something from add, subtract, multiply, and divide, which is what a polynomial does with whole powers, doesn't have any fractional powers in there, then you can start to approximate, right? Yeah, they'll program it in to make sure that what it shows is accurate. So like 9-digit accuracy. I think I mentioned before, like you might think that it just stores all inputs in there somewhere for all possible outputs, but even just if you have a 9-digit accuracy for sine, to contain all of your inputs and outputs just from 0 to 1, it takes 20 gigs of memory to do that. So it's a whole bunch of numbers. So it has to do some calculation to get that for. Another way of thinking about what we're doing is, let me take a step back. We have different representations for numbers. For example, when we have a square root of 2 or pi, that represents, we can write the square root of 2 down with a symbol, and we know what number that is. It's the number we can square and get 2. But often in calculations or in practice, we have to actually put down a value in a decimal representation or a fractional representation. But there's no fractional representation of the square root of 2. But we have a decimal representation that we can use, and we can just keep adding on as many digits as we need for the accuracy that we care about at the moment. That's exactly what we're doing with functions right now. We have functions that are kind of hard. We can write down sine of x, but when it comes to actually calculating or solving certain kinds of equations, that doesn't work really well. But we're able to start building polynomials that we can just go out as far as we want, that will get us the accuracy that we need for whatever our application is at that time. So we're basically building the kind of decimal approximation that we love for numbers into functions so we can get these polynomial extensions and get as accurate as we need. Okay, any questions? All right. So let's go back to, let's do the iClicker problem. So here we have the square root of x, that's our function. The derivative is 1/2 x to the minus 1/2. And the point that we care about is 4. We care about it at x equals 4, or a, we call it the center, is 4. So f of x, f of 4 is 2, f prime of 4 is 1/2. 4 to the minus 1/2, which is 1 over 2 times 1 over 2, which is 1/4. So here we have our slope. So y minus y1, which is 2, equals 1/4 x minus x sub 1, which is 4. And you can add 2 to both sides. You get that. That's one representation. You can expand that out and get the other one. So I know some of you would do y equals 2x plus, y equals 1/4 x plus b, and then you take your point 4, 2, plug it in for y and x, and you have to solve for b, and you get b equals 1. So y equals 1/4 x plus 1. So either of these were correct answers on the iClicker quiz. So they were C and D. Okay. Now, the reason I had you do this is these two different representations are nice for different reasons. This one is nice if we want to know where the intercept is at x equals 0. But this one is nice if we want to know about the value at x equals 4, not at x equals 0. Because when we plug in x equals 4, then this term goes to 0, and we just have 2. And this is going to be the trick that we use when we are finding polynomials not at 0, when we have to use a different center that isn't 0. We actually can't use 0 for the to find Taylor polynomials for this function. It's defined there. You can plug in a 0, you get out a 0. But what's the derivative at x equals 0? It's undefined. It's infinite there. We can't start building a Taylor polynomial from there. So we have to find another center to build it from. Okay. And the centers, so if you're centered at x equals 0, then your polynomials are going to look like Tn of x is going to be f of 0 plus f prime of 0 x plus f prime of 0 over 2 x squared plus f double prime, oops, that's double prime, triple prime of 0 over 3 factorial x cubed dot dot dot. Okay? Why do I have to divide by that the 2 and the 3 factorial here? So he said you have to get rid of the coefficients that are going to come up when you take the derivative that many times. If I start taking the derivative of this, when I multiply by 3, I'm going to, like in this term, I'm going to have 3 third derivative of 0 x squared over 3 factorial. And then when I take the derivative again, then I'm going to have 3 times 2 times the third derivative of 0 times x over 3 factorial. And if I take it again, third time, I'm going to just have 3 times 2 times f, the third derivative of f 3 factorial, plus some other stuff that have x's in it, and those will cancel out. And all I have left is the third derivative at 0. And at x equals 0, all of these other terms have x's in them. All the other terms. So at x equals 0, what happens to these terms? They are gone. So the third derivative is of the Taylor polynomial is exactly the third derivative of the function that we're trying to map. So, okay, that's if we're centered at 0. The polynomials look a little bit different if we are centered at, if we're centered at something else. We're going to do the trick that we did with the iClicker quiz. Instead of writing in terms of x, we're going to write it in terms of x minus a center. So at x equals a, our Taylor polynomial is going to look like the function value at a, the derivative at a, but multiply it by x minus a. Second derivative at a over 2 multiplied by x minus a quantity squared. Third derivative at a times x minus a cubed, but divide by 3 factorial. Dot, 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 dot. So here we're building this polynomial, but in terms of powers of x minus a. Okay. Now, I've done a lot of talking. Let me give you guys a problem to work on. So, you've already started this problem. Give me the third degree Taylor polynomial centered at x equals 4 or a equals 4 for the function y equals the square root of x. Okay. you have questions about anything we've done since Tuesday, related to these scalar polynomials, all one of several, explain to you. I'm sure a lot of you have questions right now. Okay, so I didn't leave enough time for us to work through all this, but let's try this. I did put on the equation that we got from the iClicker quiz, 1/4 x minus 4 plus 2. What's the next term we got? We should have an x plus 4 squared. I'm sorry, x minus 4. Come on. Ah! I hate technology. So plus x minus 4 squared but we need to give this a coefficient. What was the coefficient you guys came up with? A negative what? A negative 1/16? 1/64? Wow. So that gives us a cubic that seems to fit better right there. Okay. What about the next one? Plus 1 divided by 512. Oops. I must just have big fingers today. 1 divided by 512 times. Dang it. Well, we'll finish. It works out really well. There. Have a great day. We'll continue this on Monday. Enjoy your weekend. Well, it would have been okay if the technology would have been working. At least it did for some part, which was an important part. But I like to move the center when you get the tangent.
The issue during the phase, he's trying to take the courses that would count for engineering as well as computer science classes, and then he just kept taking a few more computer science classes as well as electrical. You're welcome. And if you have questions on you should definitely check my arithmetic. Okay. So to make sure I added up your points correctly. So, yeah. Oh. Yeah?
Actually, I found the convert to be less than 1, but it says 0 and then that missed 2 questions because of this. On the comparison test.
With the integral?
Yeah, there was the 2 questions where I could use p-test to solve.
Yeah?
Yeah.
Dang.
Well, I got the things right I expected to, and things
Wrong
that I expected to as well, so I mean, I know what to study, so.
Yeah. Well, that's good. Yeah.
Thank you.
You're welcome. So why are you taking this, why are you sitting in?
Oh, because my math was not really good when I was in college. I just wanted to relearn.
Okay.
Yeah.
You're not planning on getting another degree or anything?
Actually, I don't think will have sufficient time because I'm working right now. And then the every day I do only 3 things: work, sleep, and math. And I don't know if that's only 1 class.
Right.
Yeah, I don't know if I have.
But since you work here at BYU, you can start taking classes for free. So you could, get in a graduate program or something. So you can think about it. So,
I really appreciate your time. I mean, allow me to attend your class.
No worries. Fun to have you in here.
Thank you.
Yeah.
And then if I have questions, can I come back?
Yep.
Have your list to use.
Yeah, absolutely. Absolutely.
Thank you so much.
You're welcome. Okay, see ya.
See you.
Did you have any questions?
Not so far, I'm looking forward to it.
You should go ask John what that is.
sure.
That's very appreciated. All right.
Well, thank you. Have a good day.
You're welcome, you too.